Okay, Assalamualaikum warahmatullahi wabarakatuh. So we continue with chapter number 3, Dynamics of Biomolecule. So we're going to see the stochastic theory of reaction rate, not so deep. Conventional explanation of protein, okay, and introduction to polymer biophysics. Okay, first, these are stochastic theory of reaction rate, but I believe this one is for master student. So if we want to go deep into this theory, okay, Langevin, uh, Uhlenberg, whatever, Marcus theory. Okay, so but here we can see that uh, we have this unimolecular reaction, so R and P, so changing from one state to another state, okay, from A to B or from open to close. Okay, so we have here direct. So R for reactant and P is for the product. Okay. So here if we from this picture we see that in order from R to become P or the reactant to become the product, so it become or it can go to the transition state or the meta stable state. Okay, so meta stable state in our nuclear physics. Okay, so before it move become a product, so it is in meta stable state. Okay, so here we can see that there is two type. If the transition state comprise of all the substate in R and P, so direction has fluctuation barrier. So R need to exit this barrier before it can become P. Okay, so our activation energy. And if the transition state are reduced to single conventional substate, direction is gated. Okay, so meaning that on or off. Okay, so that is for the. So here is the example R and P, R to P reactant to product, or A to B, open to close. So here we can see that it can be for C6 uh, carbon. Okay, so you can see in both conformation or in chair conformation with the reaction rate Ka and Kb. Okay, so if Ka is greater than Kb, so we are going to have a lot more of chair. But if Kb is greater than Ka, so we are going to have a lot more boat than the chair. Okay, so these are the reversible reaction. So the equation again, A and B or R and P, Ka, Kb. Okay, so you can see here we have the activation energy. Okay, so the reactant R must exceed this activation energy to become a product. If the reactant only in the metastable state only at this point, so it will still act as reactant, not a product. But if the reactant, the metastable state is at this point, it can be reactant or it can be product, depend on if it can move to this side. Okay, so the reaction coordinate. Okay, so using our math method, first order ODE. Okay, so you can find the same equation in our ODE. The spring constant, for example, the spring constant, the same. Okay, so the solution for this reversible reaction, so the concentration of A and the concentration of B. Okay, so these are the equations. So depend on time. Okay, so here we can see that if we assume that at t equal to 0, there is no product. So the product is 0. All are reactant. R, so reactant is 1. So but when the reactant changing to the product, so the reactant concentration will go down, and the concentration of the product will go up, and until after some time. Okay, so you can see here these are the the equilibrium. Okay, the concentration for each reactant and the product. Okay, so these are uh, that reaction, the reaction, and this one is for the conformational transition. Just like we say that here, from this conformation or from this configuration to this configuration. Okay, so here the example is myoglobin. Okay, so from our blood, myoglobin in our blood with the carbon dioxide, okay, attached, so it become the metastable. Okay, so this metastable can become a stable one, MB0, or it can go back to the reactant MB plus CO2. Okay, kalau dalam contoh yang paling senang, and the one that I like to say to my previous student, okay, these are two people, male and female, and these are a couple. Okay, bercouple, bercouple boleh berpisah jadi dua orang beza lagi, bercouple, berpisah, bercouple, berpisah, bercouple, berpisah, but here ni dah jadi berkahwin. Okay, so MbCO, these are irreversible. Okay, irreversible. Okay, rubber monoxide binding to consists of two steps: biochemical reaction of ligand, absorption from the solution, and unipolar reaction of the ligand, covalent binding to heme from the protein interior. Okay, so here, but we do not. These are just example, but we don't want to become myoglobin this CO because keracunan gas carbon dioxide. Okay, and this one is the example. Time dependence of rebinding of CO molecule after photo dissociation of CO bound sperm whale myoglobin at various temperature. This one we bleach or photo dissociate this CO, and we want to see how fast it will combine back become MbCO. Okay, depend on the temperature. Okay, so here we can get the fastest one is 108K, 60K will be different. Okay, a random walk. So in even in SPS4120, so we can refer it there. Okay, next is the polymer biophysics. This again in our SPS4121. We also have this. Okay, so polymer or poly in this case, or in this molecule, polypeptide, a chemical compound with very high molecular weight. Okay, so these are polymer. So we can consider polypeptide as polymer. So in organic chemistry, in polymer usually we talk about polymer physics. Contohnya getah tayar. Okay, so how can we make the polymer to become strength? Okay, or the top glove, sarung tangan. Okay, so that is also the polymer. So polymer are long chain molecule form of a large number of basic repetitive unit called the monomer. Okay, so polypeptide is peptide is monomer, polypeptide is polymonomer. Okay, so here we can see the linear branch as in our lecture week 1, lecture number 2, I believe. So we have star, ladder, and these are also the composition of some polymer. So if we had a polypeptide, so this one is C, 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 C. So how it uh, 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 maknanya dia berputar ke polypeptide tu, kedudukan polypeptide tu. Okay, so we have model. Okay, so the first one is free jointed chain model. Okay, so maknanya in this bond can move around freely 100 not 300 nearly 360 degree moving. Okay, so the end to end length re of the chain. Okay, so this one from here to here, so is equal to this is this formula. Okay, so n b naught. Okay, so this b naught is the length of this one. Okay, length of between C and C. Okay, so if we take the average of b naught, so we get this one. Okay, and n is the number of monomer or the number of this C, C, and so we can see the initial carbon and the final carbon, where the distance between that initial and final carbon. Okay, and this one is random flag chain model. Uh, this one not is, you can see that the previous model 360 degree, nearly 360 degree, but here we have a fixed angle. Okay, the carbon can only move at fixed angle. Okay, so then the end to end, the initial C to final C is equal to this equation. Okay, so we can try to prove this. So we have NB. So again, if alpha equal to 0, then it becomes again as NB naught square. Okay, so we have this. And a Kuhn segment. Okay. Okay, so a segment is a statistical unit with its physical position independent of adjacent unit. Okay, so here one segment, so we can get this length, this one, this length, and this length. Okay, so LK, the Kuhn segment equal to RE squared over RM squared. Okay, so these are the length of this segment divided by the average end-to-end length divided by this. So we have the Kuhn segment. Okay, so meaning that we can, to make our life easier when we do the calculation or the modeling, or using the computer to calculate the end-to-end, so we can divide the polypeptide or polymer into some segment. Okay, so let's say this one 1 2 3 4 5 6 1 2 3 4 5 6. Okay, 1 2 3 4 5 6 1 2 3 4 5 1 2 3 4 5. Okay, so you see most of the polymer are divided by to 6 monomer. Okay, so we have the Kuhn segment. And then effective length and persistent length. So the first is effective length or chain stiffness. Okay, so we can calculate using this b squared b naught squared 1 plus cos alpha 1 minus cos alpha equal to b naught c infinity. Okay, so this effective length is that we have the length for because we know that the between this carbon and carbon we will have a vibrational. So kalau dia stretching, dia lebih length dia lebih panjang. Kalau dia uh, uh, mengecut, length dia lebih kecil. Okay, so we take the middle or the average of this length. Okay. Okay, and the persisting length equal to 1/2 of the Kuhn segment. Okay, so this one is the, again we can say that these are the average length of the Kuhn segment. Okay, persisting length, this length we can see. Okay, so from this we can estimate, okay, from this calculation or from this formula or this formula we can calculate how big is the polypeptide. Okay, even though we say that the polypeptide is a very long chain, but when it coagulate or it do the folding, so what are the shape of the polypeptide, or in for our case protein or nucleic acid. Okay, so we can estimate the radius of the polypeptide. Okay, so next is the ionic current through electrolyte. Okay, so here this one we what we want to say here is that from biomolecule, okay, so it can act as a wire and it can move the electron around from one side to other side. Okay, so here or in our case or in our body we have a signal, we have a neuron. Okay, so daripada sensor, from the sensor, let's say the touch the from our lidah kalau kita rasa. Okay, so the the rasa, okay, the rasa will change into the electrical current, and that electric current will be moved from our neuron to our brain to be interpreted by our brain, whether rasa masin, rasa masam, or anything. Okay, so we have this electric current. So electric current itself is carried by the mobile ion of electric solution. Okay, the relationship between electromotive force E and electrolytic current I is again the Ohm law, E equal to IR. Okay, so let's say these are neurons, so moving from one side, for the electron moving from one side to another side. Okay, so we have this. Okay, and in moving the information, moving the electron from our sensor to our brain, so we have the resistance. Okay, so resistance depend on the dimension of the electrolytic cell. Okay, depend on our, kalau contohnya kalau dia melalui darah banyak electrolyte. Okay, so depend on that resistance of that electrolyte in our blood. Okay, so example, R equal to resistance equal to rho L over A. Rho A is the cross section of the plate. Rho is the resistivity of the electric cell. Okay, and this length is the typical order of magnitude of resistivity for body fluid is about 1 ohm per meter. Okay, so how fast the signal from our sensor is passed through the neuron to our brain. Okay, kalau lambat dihantar, maknanya lambat dapat jawapan. Okay. Okay, electrical conduction by ion is less effective than conduction by the electron. Okay, so electrical conduction by ion is less effective because ion lebih besar, ion is big, so sometimes we make loss in the way to the brain. We will loss. Okay, so it's better by the electron. Okay, conductivity sigma of the solution as a function of salt concentration. So here conductivity of this solution. So these are just a Taylor expansion. So we can see the Taylor expansion. We have the equation sigma c kappa 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 c minus kc c 3 over 2. Okay, conductivity of electric solution is proportional to ionic concentration or low salt concentration. So here these are concentration. So low salt concentration. If this C small, so it depends on the concentration. C, C, C. If it's C small, the conductivity also will become small. Okay, C increase, conductivity also increase. Okay, so molecular infinite direction only depend on the kind of salt used. Okay, so here we have the various ion. Okay, value 34.9, 7.4, 7.6, 5 point. So this. Okay, so here we can see that the quantity for H plus is much better than the ion. These are the ion. These are the proton. So we say this is a proton. So proton moves much faster than K plus. Okay, so we can also model the ionic current using the division. So F outer force, F equal to QE. Okay, so if we have magnetic in our outside our body, okay, so the resistance force Fs equal to 6 pi eta R V bar. Okay, so the velocity of ion passing by, so V bar equal to mu Q times E. Okay, so this one using this and this, so we can get this V Q E. And the current passing by the molecule I equal to A over L, the cross section of the plate, and the electrophoretic mobility of the molecule. Okay, E times delta V, the volume. Okay, so meaning that we can calculate the current from either from this EIR or in this biomolecule using this equation. Okay, so in order to send the signal from our sensor to our brain to be interpreted, so we have this electron conduction and tunneling. So energy transfer by charge carrier is the most common reaction in metabolic process. So these are the example redox reaction. M naught. So passing, this one is passing electron from one molecule to one molecule. So here these are reduction and oxidation reaction. Mg naught DH plus DHCl plus, so Mg plus H2 naught. Okay. So here, how can the charge or the transfer? In this case, is the proton. So you can see here, these are the proton. So this OH, then if the H is passed to this oxygen, so it become OH and O. Okay, so how can it pass this hydrogen or this proton moving from this oxygen to this oxygen? Okay, so here we can see that if the energy barrier, the vibration energy is the same as the energy barrier, so H can be at this oxygen or at this oxygen. If both are in the same energy potential, OH and this AH. But here, for this, okay, in quantum mechanics, we know that even though this molecule cannot pass through this energy barrier, but it can do the tunneling, moving from this part to this part A. Okay, so these are the charge transfer, the tunneling. Okay, so charge transfer mechanism, sending the signal again from our neuron or from our sensor to our brain. So the proton moving from one molecule or from one carbon residue to one carbon residue. Okay, so a transfer of proton impurity H plus, acceptance of electron is rejected by donor molecule D, formation and transport of charged radical H plus, and ejection of electron from protein molecule with charged radical H plus. Okay, so here these are the Franck-Condon principle. Okay, so you move to this point and then goes to this point. Okay, so ground vibrational state to the excited vibrational state, and then move to the electronic state. Okay, excited state. Okay, so we have this transition or conduction. Okay, the last one. Okay, so the example, the proton channel of cytochrome C oxidase from R spheroides. Okay, kita tak penting pun apa maksud dia tu. Ini, this one. But here we can see that this one, H plus moving from this oxygen or from this C to 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 this C. Okay, so let's say these are our sensor, and this is our brain. Okay, so the information is moving from here to here through this proton channel. Okay, so these are the membrane and the protein. Again, this one. So this one moving, you can see here moving to here, but at point patah balik, buat U-turn, patah balik. So this one will take a long time, but this one will be much faster coming to the brain. Okay, so I think that's all for chapter number 3. Thank you.